In this lecture video, we're going to look at inferences about a population proportion using a simple random sample. Now consider a finite population consisting of cap n members. Suppose that we are interested in the proportion of members in this population that have some characteristic of interest. Denote this proportion by p. In general, the proportion p will be unknown, and our interest will center on making inferences about it. Now for the kth member of this population, k going from 1 up to cap n, define the variable u sub k in the following way. It's equal to 1 if member k has the characteristic of interest, and it's equal to 0 if member k does not have the characteristic. Then the resulting population of values, the set of values u1, u2, and so forth up to u sub cap n, are then 0, 1 variables that indicate whether or not each member of the population has the characteristic of interest. Note that the population mean of this indicator variable, which is denoted by mu, if we think of it as a population mean, being 1 over cap n times the sum of the u variables, that is equal to the number of the members in the population that have the characteristic divided by the number of members in the population, which is just p, the proportion of members in the population that do in fact have the characteristic of interest. Now to note the population variance of this variable by sigma squared, it can be shown that sigma squared also depends on the population proportion, p, and in particular is given by the following expression. The variance is equal to p times 1 minus p. So both the population mean and the population variance of this indicator variable are functions of the population proportion, p. Now our inferences about p will be based on sampling from the population of indicators. Let x1, x2, and so forth up to x sub little n be a simple random sample of size little n from this population of indicators, and let x bar denote the sample mean. Now from previous results we know that the sample mean is an unbiased estimator of the population mean, and what that implies in the current context is that the expected value of x bar, in other words the mean of the sampling distribution of x bar, being equal to mu is also equal to p because mu is equal to p. It follows in this context that the sample mean is an unbiased estimator of the population proportion. Using the hat notation that we've been using, we'll use that to denote the estimator of p. We have p hat equal to x bar, the mean of the sample of indicators. So p hat is an unbiased estimator of the population proportion. Now we need to consider the variance and standard error of p hat. And so let's take a look at this. The variance of the sampling distribution of the estimator of the population proportion, in other words, the variance of the sampling distribution of p hat, will be denoted by sigma squared sub p hat, as well as by var of p hat. And it can be shown that the variance of p hat is equal to this expression here, that, as you can see, depends on the population size, the sample size, and the variance of the population of indicators. And so this is equal to cap n minus little n over cap n minus 1 times 1 over little n times sigma squared. And because sigma squared is equal to p times 1 minus p, as we indicated on the previous slide, right, the variance of p hat is given by this expression. The standard deviation of this expression gives us the standard error of the estimator of the population proportion. And so this expression here down at the bottom gives us the standard deviation of the sampling distribution of p hat. Now we're not able to calculate sigma squared sub p hat exactly because it depends on the unknown value of p. So we have to estimate it, and we do this by plugging in our estimate of P. We plug in P hat for P, and so that gives us an unbiased estimator of the population variance. I'm sorry, before we get there, an unbiased estimator of the population variance is given by this expression. So cap n minus 1 over cap n times the sample size, little n, divided by little n minus 1, times p hat times 1 minus p hat. Okay, and so once we have that, we can replace the unknown sigma squared by sigma hat squared. Okay, and so that gives us then the estimator, in fact an unbiased estimator, of the variance of the sampling distribution of p hat. So an unbiased estimator of the variance of the sampling distribution of the estimator of the population proportion is given by the following expression. Now notice that I've put a hat now on sigma squared, all right, because this is an estimator. So the estimated the estimated variance of p hat, so sigma hat squared sub p hat, is equal to cap n minus little n all over cap n times 1 over little n minus 1 times p hat times 1 minus p hat. So this is the estimated value of the variance of the sampling distribution of p hat. Now that we have this, we can take its square root, and that gives us the corresponding estimator of the standard error or standard deviation of the sampling distribution of p hat. And so it's just the square root of this expression. Now, once we have the estimated standard error of p hat, we can calculate the approximate 95% margin of error associated with p hat. That is given by twice the estimated standard error of p hat. So 2 times sigma hat sub p hat, which is 2 times the square root of cap n minus little n over cap n, times 1 over little n minus 1 times p hat times 1 minus p hat. So again, this is the margin of error for an approximate 95% confidence interval estimate of the population proportion. And so once we have that, along with our point estimate of p, which is p hat, all right, we subtract this quantity from p hat to get the lower end point of the interval, and then we add this margin of error to p hat to get the upper end point of the approximate 95% confidence interval. And so that is what is given down here at the bottom of the slide. So you see again this common progression. We first come up with a point estimator for the parameter of interest. We then identify the variance and standard error, the true variance and true standard error of that point estimator. The standard error and the true variance will depend on an unknown population parameter, and so we won't be able to compute the variance and standard error exactly. What we have to do is estimate it by estimating the unknown parameters in its formula. Once we do that, we're able to come up with an estimated variance and an estimated standard error for the point estimator. Once we have that estimated standard error, we can multiply it by 2 to get the approximate 95% margin of error associated with that point estimate. And then once we have both of those pieces, the point estimate and the margin of error, then we can construct a confidence interval estimate for the parameter of interest. So let's look at an example. The Fish and Game Department in a particular state wanted to determine the proportion of hunters seeking any type of game bird. A simple random sample of size little n equal to 1,000 of the cap n equal to 99,000 licensed hunters in the state was obtained. Suppose that 430 indicated that they hunted game birds. Estimate P, the proportion of licensed hunters seeking game birds, and calculate the approximate margin of error for this estimate. All right, so cap n, the population size of licensed hunters, is 99,000. The size of the simple random sample that has been selected from this population is 1,000. Of the 1,000, 430 indicated that they hunt game birds, and so that is X. P hat, the point estimate for the proportion of hunters that hunt for game birds, is given by X over N, so 430 over 1,000, or 0.43. So that is our point estimate for the proportion of hunters who hunt game birds. Now we want to go beyond a point estimate though. We want to quantify the level of variability associated with p hat, and we can do that by calculating the estimated standard error of p hat. And so this is the formula that we use, and again it's based on the population size, the sample size, and the point estimate itself, p hat. And so once we plug those values in, we see that the estimated standard error of p hat, which again is the estimated standard deviation of the sampling distribution of p hat, is 0.01558. Now, once we have the estimated standard error of p hat, we can multiply that by 2 to get our approximate 95% margin of error associated with p hat. And doing that gives a margin of error, an estimated margin of error, of 0.03117. Now, although the problem didn't ask for it, it didn't ask for a 95% confidence interval, once we have the point estimate and the margin of error associated with that point estimate, it's very easy to come up with the confidence interval, the approximate 95% confidence interval. Again, we just subtract the margin of error from p hat to get the lower end point, and that would be about 0.398 or 0.399 for the lower end point. And then to get the upper end point, we add the margin of error to that point estimate, 0.43 plus 0.03117, and that gives an upper end point of about 0.461. All right, so an approximate 95% confidence interval for the true proportion of hunters who hunt game birds would range from 0.399 to 0.461. So we could say that we are approximately 95% confident that the proportion of hunters who hunt game birds is somewhere between 0.399 and 0.461. All right, next we will look at how to determine the sample size to be able to estimate a population proportion with a specified margin of error. So suppose that a simple random sample is to be selected from a finite population of size cap n and with unknown population proportion p for the purpose of estimating the population proportion. Now the sample size needed to do this, to estimate the population proportion with an approximate 95% margin of error equal to E, is given by the following expression. So 4 times p times 1 minus p times the population size cap n, divided by 4 times p times 1 minus p plus cap n minus 1 times the square of the desired margin of error. Now the problem with this formula from a practical standpoint is that it depends on the very quantity that we don't know and that we're wanting to estimate, and that is the population proportion p. Now if we have a separate estimate, p hat of p, available, say from a prior study or something like that, by which we get a ballpark idea of what p might be, then that prior estimate can be used in place of p to obtain an estimated sample size to obtain. And so if we had, for example, a pilot study or preliminary study or previous study that we can use to come up with a value for an approximate value for p, then we can plug that value p hat in and then come up with an estimated sample size to use for the sampling purpose at the present time. Okay, now, but if the problem is if we do this, that if the true value of p is no longer close to this previous version, or the estimate p hat from the previous study, then the actual margin of error may be larger than that which is desired. So that would be undesirable, obviously. But if, on the other hand, if no prior estimate of p is available, then what we can do is use a conservative sample size, which we do by using a conservative, plugging in a conservative value of p. And so the formula that would be conservative would be using a sample size given by cap n over 1 plus cap n minus 1 times the square of the desired margin of error. Now, this sample size is conservative in the sense that the margin of error obtained from a sample of this size is guaranteed to be no larger than the desired margin of error, cap E, and it may very well be quite a bit less than cap E. All right, so let's apply this. So this is example 11. The Fish and Game Department in a particular state wants to determine the proportion of hunters seeking any type of game bird. So this is the same kind of situation that we had before, but we can think of this as being at the planning stages before we've ever even collected any data. And so they are wanting to determine the sample size required to be able to estimate the proportion to within a given margin of error. Now, again, suppose that there are 99,000 licensed hunters in the state. And so the problem is, the question says, determine the sample size needed to estimate the proportion of hunters seeking any type of game bird with a margin of error of no more than 2% or 0.02. All right, so the population size is 99,000. Again, the problem here is to find the sample size, little n, such that the margin of error is no more than 0.02. Now, we're not given a prior value for p, and so we're going to use this conservative formula to get the sample size. And so that is, again, equal to cap n over 1 plus cap n minus 1 times the square of the desired margin of error. So 99,000 all over 1 plus 99,000 minus 1 times 0.02 squared. And when we evaluate that, we get a sample size of 2,438.45. And since we cannot have a fractional sample size, we use the next larger integer, 2439. And so if we were to select a simple random sample of that size, then we would be guaranteed that the margin of error that results will be no larger than 2%, and as we indicated, it may be quite a bit less than 2%. So that wraps up our coverage of inference procedures for a population proportion based on simple random sampling.